In the last few days, we've been spending quite a bit of time talking about the first derivative, right? What do we get from the first derivative? We get those critical points. Those critical points give us intervals of increase and decrease, which then gives us maxes and mins. Today, we're going to talk about what, if anything, we can get from the second derivative, or f double prime. So before we do that, let's do a quick little review of vocabulary. Here's this lovely graph, and it says determine where, which would mean x values, the above graph is concave up and concave down. Now these terms should be familiar. We talked about them last year in pre-calculus. So we talked, or if you had me, we said concave up looks like a cup, whereas concave down looks like a frown. Okay, so by the way, unless something is linear, it is either concave up or concave down. So there's no linear part of this graph, which means we need to look at the entire thing as a cup or frowning, smiling or frowning. Okay, so again, this approximately where is going to be helpful, but I would say it looks like I'm frowning like kind of in here. And at some point, I didn't really match up my colors, did I? Sorry. I used red for that's okay. It looks like I'm smiling or concave up everywhere else, right? So I switched my colors. I apologize. But the idea is it looks like we are concave up from, these are intervals, so x values, from negative infinity until about 0. And then it looks like, again, let's just kind of call that 3, right? Looks like it changes somewhere in there. 3-ish to infinity, which means we are concave down from 0 to 3. Now, if you recall last year from pre-calculus, the place where the graph changes concavity, we call those inflection points, or you could call them points of inflection. Same thing, where the graph changes concavity. Okay? All right, so that's just a quick little review. So, leads us into what we're going to talk about today. So it says, yes, we can get a lot of information about the original from f prime, but it is not enough. If I know that a graph is increasing, it still doesn't tell me what the graph looks like. Because if a graph is increasing, it could either be a line. So, by the way, if it's a line, we're not using calculus to graph it. But if it's a curve, it can increase in two different ways, right? We could look like this, or we could look like this, right? And this really goes along with what we were just talking about. This is smiling. This graph is concave up. This graph is frowning. We would say it is concave down. Again, we could also have a linear function, but we won't use calculus to graph a line. All right, so this is case number 1. Let's take a look at what is happening with case number 1. Let's think about the spaghetti. Let's think about the tangent lines. If I were to draw in, like, say, 3 or 4 tangent lines, as we read the graph from left to right, what could you tell me about those red tangent lines? They are positive, right? The slope is positive. I think we could also say they are increasing, right? As I go from left to right, the slopes are getting bigger. So I'm going to write that down. Slopes are increasing. Okay, well, let's do the same thing with my second case. Let's look at some tangent lines there. Maybe a tangent line here, maybe here, and maybe out here. I think we could say the opposite. Here we would say the slopes are decreasing from left to right. That's how we read graphs, right? Where do we get slopes from? The first derivative. So I'm just going to do a little bit of translating. Instead of saying the slopes are increasing, I'll say f prime is increasing. Likewise, if the slopes are decreasing, that means the first derivative is decreasing. And just in general, if a function is increasing, we've been saying this now for 2 days, if a function is increasing, its derivative is positive. Well, our function is f prime. F prime is increasing, so its derivative is positive. Or above the x-axis. So this is how we start tying in the second derivative. When the second derivative is positive, our graph will be concave up. Our original will be concave up. Okay. Let's look at case number 2. If f prime is decreasing, then its derivative will be negative. And that tied in with the graph being concave down. Okay. These are really, really, really big connections. In fact, let's take a look at our third slide. I kind of wrote it all down for us here. Okay. So when the second derivative is positive, my original is concave up. It looks like a cup or it is smiling. When the second derivative is negative, that means f of x is concave down. At the point where the second derivative changes sign, right, f of x has a point of inflection. Right? If the second derivative is changing sign, that means the original is changing concavity, which means we have a point of inflection. I will come back to this statement here on the back of our notes. Okay. So if we would like to know when the second derivative is positive, when the second derivative is negative, we first need to know where the second derivative is equal to 0 or does not exist. It's like finding critical points, but this time we're using the second derivative. Okay? Procedurally, everything's going to be the same. We're just going to be using a different derivative, which means it's going to spit out different information. So just like we had the first derivative test that gave us intervals of increase and decrease, we will now have a second derivative test that will give us intervals of concave up and concave down. But procedurally, it works exactly the same. All right, here's our first example. Find the inflection points and determine where the curve is concave up and concave down. All of this information comes from the second derivative. So let's find the second derivative. So I've got 3x squared minus 12x plus 12. That's the first derivative. The second derivative is 6x minus 12. I am going to set that equal to 0. Of course, you can do that in many ways. I'm also going to ask, where does it not exist? Well, guess what? It's a line. It exists everywhere. There's no holes. There's no jumps. I'm not going to call it a critical point because technically it's not coming from the first derivative. But regardless, this is going to be my second derivative test. So let's label it as the second derivative because that's going to tell me exactly where to plug things in. I want to know what is the second derivative doing here and what is the second derivative doing here. So let's plug in, I don't know, let's plug in a 0 into the second derivative. I like the factored form better. That's up to you. 6 is always positive, so I'm going to ignore that. If I plug in a 0, I get a negative. If I plug in, like, I don't know, a 3 or a 4, I'm going to get a positive. Okay, which means my graph will be concave down from negative infinity to 2. My graph will be concave up from 2 to infinity. See how I changed concavity there? Which means I have an inflection point when x equals 2. Just like a max or a min, an inflection point is a point on the graph. That's why they want us to find the y-coordinate as well. How do we find y-coordinates? We go back to the original just like with maxes and mins. So I'm going to go plug in a 2, and I get 8, minus 24 plus 24? Oh, perfect. So my inflection point is at the point 2, 8. And there's everything they asked for. So again, the procedure looks exactly the same. We're just using the second derivative instead of the first derivative, which means my intervals represent something different. Okay. All right, I'm going to flip it to the back. You pause if you need to. So let's kind of take a step back and make sure we define or check our definition. It says, for the function defined by f of x equals 1 over x, does an inflection point actually exist? Okay, well, we could do this a couple of ways, but let's use the derivative, right? If y equals x to the negative first, y prime equals negative x to the negative second, y double prime equals 2x to the negative third, which, I know, let's clean that up. So we have 2 over x cubed. So I'm going to ask, when does the second derivative equal 0? Well, never. And I'm also going to ask, when does the second derivative not exist? Which means I'm looking at the denominator, and it looks like I'm going to have a problem at x equals 0. I'm just going to jot that down. X equals 0 is a place where the second derivative does not exist. Well, that means it needs to go on our second derivative test. Perfect. Let's go pick a number to the left of 0. I don't know, like -1. And remember, we're plugging into the second derivative, right? If I plug in a negative, I cube it, it's still negative. And a positive divided by a negative is a negative. Pick a positive one, cube it, still positive. A positive divided by a positive is a positive. So I see that we're concave. They didn't ask us to do this, but I'll do it anyways. We are concave down from -infinity to 0. We are concave up from 0 to infinity. Do you see how I change concavity here? So, oh, there's an inflection point at x equals 0. Right? We changed concavity, and an inflection point is where we change concavity. Try plugging in the 0. 1 divided by 0, uh-oh, that's a problem. So no, there is no inflection point on this graph. We did change concavity, but to be considered an inflection point, it actually has to be a point on the graph. And by the way, I'm going to flip our notes back over. That's what I was referencing right here. When f double prime changes sign, we have an inflection point if this point is in the domain of f. That's the problem we ran into. 0 was not in our domain. It was still an important place for us to look at because we changed concavity. It's just there's no point there. Okay, so there are times where we will change concavity and not have an inflection point. Okay, this slide is blank because I just didn't need it. I moved this one down here because I wanted to just give us extra room. Okay, all right, so here we go. Very similar to what we were doing yesterday or in our previous lesson, but I've just added an extra couple of things to it. So we're going to state the domain, find the intercepts, intervals of increase, decrease, maxes and mins. All of that comes from the first derivative. Find the intervals of concavity, find the inflection points. So those two things come from the second derivative. And then we're just going to put it all together and get a real sweet graph. All right, so here's my function. It's a polynomial, right? Its domain is all real numbers. So we're not going to have any domain problems. And then we threw this in. Find all the intercepts, x and y intercepts. Let's do that here. If you want to find an x-intercept, we plug in a 0 for y. I don't know, let's factor out an x cubed. So I have x-intercepts at 0 and 4. You know, I'm going to box that in because that's something I'm going to put on my graph in a little bit. A y-intercept, we plug in a 0 for x, which is 0. Okay. So there's my y-intercept. Well, that's not very helpful because the same thing. That's okay. All right. So the next thing is to do our first derivative test. So here we go. F prime of x equals 4x cubed minus 12x squared. I'm going to ask, when does this equal 0? And that happens at 0 and at 3. And I'm also going to ask where it does not exist. It's a cubic. It exists everywhere. There's no radicals, there's no logs, there's no denominators. So these are my critical points. X equals 0 and x equals 3. Well, let's go ahead and get our sign chart here. This is my first derivative. Something interesting is happening at 0 and 3. Let's plug numbers into the first derivative on either side. I plug in a negative, by the way, I'm going here. This is always positive, isn't it? So let's not worry about that. If I plug in a negative 3, I get a negative. If I plug in a 1, I get a negative. If I plug in a 4, I get a positive. Which means my graph is decreasing and still decreasing and then increasing. I only change signs one time. And I'm changing from a negative to a positive, which means I have a minimum when x equals 3. If I want to find the y-coordinate, I want to go plug in my 3. By the way, I think the easiest thing to do is go plug it into our factored version. 3 minus 4 is negative 1. 3 cubed is 27, so I get a negative 27. Work smarter, not harder, right? Don't go in here and plug in a 3 to the 4th and then 3, factor it. So this is my minimum. But there was nothing at 0, right? We didn't, so okay. So I'm not going to necessarily write them down, but I drew them in. I'm decreasing until I get to 3. I'm increasing after 3. Okay. Whew. Well, let's do everything we just did, but now with the second derivative. All right, so here we go. F double prime of x equals, now I'm going to go back to this version, not the factored version, and I get 12x squared minus 24x. I'm going to ask, when does this equal 0? So I'm going to factor out a 12x. And I'm also going to ask, when does it not exist? It's a quadratic. It exists everywhere. So it looks like something interesting is happening at x equals 0. That pops up a lot. And x equals 2. So let's do our second derivative test with 0 and 2. Remember, if it's the second derivative test, I'm going to go plug numbers into the second derivative, which is here. If I plug in a negative 1, this will become negative. Negative 1 minus 2 is still negative, and negative times a negative is a positive. If I plug in a positive 1, I get a positive times a negative. And if I plug in a 3, I get a positive times a positive. Which means I'm concave up, then concave down, then concave up. Which means I have inflection points when x equals 0 and when x equals 2. Remember, to find y values, we plug into the original function. Well, if I plug in a 0, we already did that. We got a 0. And if I plug in a 2, 2 minus 4 is negative 2. 2 cubed is 8. So that gives me a negative 16. I'm going to box these in because these are also points on the graph. So I have intercepts, which are points on the graph. I have another point, and I have another point. 0, 0 is actually both my x and y intercept. The reason I do that is because now we can graph. We have everything we need. And if I were you, if you're not using a pencil, I'd probably switch to a pencil at this point. But let's think about the different x values we have. We've got x-intercepts at 0 and 4. We've got something going on at x equals 3, something going on at x equals 0, something going on at x equals 2. So I think for us, it's not horrible if our graph just goes from like negative 5 to 5. So like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. I can go ahead and start plotting these, right? X-intercepts at 0 and 4. Let's talk about this. Let's see, it looks like I have y values of 0, negative 27, negative 16. What if I just went from like negative 30 to 30? Maybe I just kind of chunk that into thirds, going up by tens. How's that? Okay, so my minimum was at the point 3, negative 27, so almost down to the bottom there. And then my other point, right, I have 0, 0, that's already there. And then 2, negative 16 will be kind of like in here, right? These were going by 10, so 10, 20, I'm kind of right in the middle there. Okay. All right, so I said switch to pencil. I haven't switched to pencil yet. Let's look at our sign charts. Whoops. We were decreasing until we got to 3. And then increasing. So we're going to just really very lightly sketch. I want to decrease till I get to x equals 3. And then I want to increase. Notice I'm trying to go through all 3 points there. And then that point there. Now, rough sketch. Now I'm going to put in my concavity. Remember, until I get to 0, I want to be concave up. So here's x equals 0. Till I get to that point, sorry, I'm still decreasing, but I want to look like a cup. So kind of make it smile there, yeah? Okay. Now, between 0 and 2, I want to be concave down. I'm still decreasing, but now I want to frown. After 2, we're concave up again. So after 2, I want to smile. I need to smile and decrease, and then I need to smile and increase. Now we're going to go in and smooth this out in just a second. I want to go back to what's happening at 0. Do you remember back here we had 2 critical points? That's where the slope was equal to 0. And when the slope is equal to 0, we have a max, a min, or a shelf. Well, it's not a max or a min, it's a shelf. We need to make sure that we flatten that out so that it has that slope of 0 that we were told, or that we found that it has. So just kind of go in with your pencil and just make sure there's no sharp points, no jagged edges, no lines. Right? This is a curve. This is an x to the 4th. Okay. And I think the last thing we could do is to check it on our calculator. If you're going to go type this in your calculator, I'd make your window match. Go from negative 5 to 5 and negative 30 to 30. And I think you'll find that it looks pretty darn good.